Bismillahirrahmanirrahim. Assalamu alaikum. Dear students of CS131 Discrete Structures, welcome to the next class of graph theory. In this particular lecture, we're going to be talking about graph connectivity. In the earlier lectures, I've basically talked about basics of graphs, including how do you represent graphs and some of the terminologies that are commonly used in graph theory, and that was then followed by graph isomorphism and how that is established for some examples where you can basically say that whether a graph is isomorphic or not isomorphic. And if you have to give graph isomorphism, you have to define basically the vertex mapping at the bare minimum. You'll still get full marks if you can define that. Ideally, of course, I'd like to see the exact adjacency metrics. And it is understood that for the exact adjacency metrics, the graph has already been defined. So without further ado, let's start with the next section. And in this particular one, this is chapter 10, section 10.4. And we'll be talking about a concept which is called graph connectivity, right? So let's start with the lecture. In the last lecture, we basically talked a bit, a thing about path. And I defined a path without actually giving a graphical representation of it. And showing that if two graphs are isomorphic or not isomorphic. Well, if they are isomorphic, they must actually have all paths of same length in both graphs. And if that is not true for a particular graph, then they are not isomorphic. So what is a path? Let's define it here. Let n be a non-negative integer and g be a graph, which is an undirected graph. Then a path of length n from u to v, so from a particular vertex u to v, and a path of length n in G is a sequence of n edges. So you have to define n edges starting from E1 and going on till En. So for length n, you have to define n edges of G, for which there exists a sequence and sequence of vertices such that you initialize your initial vertex x0 is from u, and you move on till xn. The final vertex in this particular path is v. Notice that there are basically start from x0. So hence there are basically n plus 1 different vertices that are possible in this path and n edges, such that ei has, for I is equal to 1 to n, the endpoints xi minus 1 and finally xi, right? So each edge has a particular edge as its endpoint, as its each edge has a particular endpoint, right? So for example, if you take this graph, in this we asked that is ADCFE a path? Well, A, D, C, F and E, well, that is a path. Yes, the answer is it is a path. What is the length? Well, the length is 1, 2, 3, 4. So 1 less than 4. Is it a simple path? A simple path is a one that does not repeat a particular thing. And I think the definition is going to come up next for a simple path. And we'll see that this is definitely a simple path, right? So which does not repeat a particular vertex again, a particular edge again. So is DCFA a path? No, it's not a path. So length is not matter because A is not directly available from D, C, F and A. F and A are not connected. Is ABED AB a path? Well, ABED AB is a path. Yes. The length of it is 1, 2, 3, 4, 5 and 6, right? So sorry, 5. 1, 2, 3, 4 and 5. 5 is the length. It is a simple path. Does it use any edge twice? Well, in this case, we notice that AB is a link that is used twice. So this is not a simple path by the definition of a simple path. So then basically, let's move on to the next few set of definitions. And I'll be kind of, defining some of these over here. So let n be a non-negative integer and G be a directed graph. So this, now G is a directed graph, a path of length n from U to V. in G. So of course, basically we want to define a path which is length n and it starts at U and ends at V. Within the graph G is a sequence of edges E1, E2 and En of G such that E1 is associated with x0, x1, E2 is associated with x1, x2 and so on, with En associated with xn minus 1 to xn, where x0 is the U and xn is the V vertex, right? So the initial vertex is U, the terminal or the end vertex is V. The path or circuit is said to pass through. So we can also call the path as circuit as well. And this circuit is different from the circuit that you're going to, maybe some of you, or at least, and I don't think so the AI guys will study this, or but the CE is for sure going to study it in at some place in the circuits course. So this is different from that circuit. You need to remember that. The path of circuit is said to pass through the vertices x1, x2, and xn minus 1, or traverse the edges e1, e2 up till en. So it traverses the edges or pass through some certain vertices. When there are no multiple edges in the directed graph, this path is denoted by its vertex sequence. So of course, if there are no multiple edges and the graph is a simple graph, it's a simple directed graph, right? So it's not a multi-directed graph, but a simple directed graph. Then we can simply give out the vertex sequence to define or to give out the path that has been used. So x0, x1, x2, and so on till xn. A path of length greater than 0 that begins and ends at the same vertex is called a circuit or cycle. So then again, a circuit is basically a path of length greater than 0. It should not be of length 0. That's a loop otherwise. And if it is greater than length 0 and it's a path that begins and ends at the same vertex, we call it a circuit or a cycle. So I'll use the word cycle. I'm more comfortable with that, but you could use circuit or something else as well. A path or circuit is called simple. Remember, it is true for both path and for circuit. A circuit is a closed circuit that starts and ends at the same point. A path, on the other hand, is it can be a circuit as well if it, but it may have different starting and ending points. So a path or circuit is called simple if it does not contain the same edge more than once. That was the exact reason why I said the last example here, A, B, E, D, A, B, because A, B edge was used twice, hence it was not simple, and that is now confirmed in this particular slide for paths. So then let's come back to these questions that we discussed there, and I kind of gave you quick answers. Is BCFEB a path? Well, BCFEB is a path for sure. Is it a cycle? Yes, it is a cycle because it starts and ends at the same point. What's the length of it? 1, 2, 3, and basically 1, 2, 3, and 4. 4 is the length. Is it a simple cycle? Well, yes, it is a simple cycle because no edge is being repeated in this. So then let's come to the next topic, which is what is a walk. The term walk is sometimes used instead of a path as well. And then the corresponding term for circuit or cycle is the term closed walk. And similarly, for a simple path, the term that is used instead in literature a lot of times is what we call trail. And however, I'm personally not in favor of using these names, and I will probably be using a different name altogether. So how do you define connectedness in undirected graphs? An undirected graph is called connected if there is a path between every pair of distinct vertices of the graph. So an undirected graph is completely connected, is connected if there is a path that is available for each pair of distinct vertices in the graph. An undirected graph that is not connected is called disconnected, right? So we can say that we disconnect a graph when we remove vertices or edges or both to produce a disconnected subgraph. So for example, let's say that this is graph 1 and we can say that this graph is completely connected, so such that each pair of vertices you can actually find a path between them, right? On the other hand, this graph G2 contains, this is a disconnected graph because we cannot find path from A, for example, to E or A to D. So again, connectedness in an undirected graph is a really simple and intuitive phenomena that you can actually guess through eyes. But for a computer program, you need to come up with the proper justifications. For example, from here, some paths may not be simply possible. So let's go to the theorem here. The theorem simply states that there is a simple path between every pair of distinct vertices of a connected undirected graph. So if there's a connected undirected graph, then there must exist a simple path between every pair of distinct vertices of that particular graph. So that brings us to the next topic, which is that of connected components. So a connected component of a graph G is a connected subgraph of G that is not a proper subgraph of another connected subgraph of G. So for example, what I mean here is that it's not a proper subgraph is, for example, BAC is one connected component. However, B and A, alone, B and A alone is not a connected component because it is subcomponent of another subcomponent of the whole graph. And hence this is not a connected component, A and B. However, on the other hand, A, B, C are for sure a connected component, which we call here H1. That is, a connected component of a graph G is a maximal connected subgraph. So you have to get the maximal connected subgraph, and that is what we define as a connected component. Some graphs may only have exactly one connected component, and other graphs like this one, this one shown on your screen, has three different connected components in the same graph. A graph G that is not connected has two or more connected components that are disjoint and have G as their union. So that's pretty much the definition of a connected component. The next important topic, and this is slightly confusing, but this is something that I've always felt is you can kind of remember by practicing it more and more, and also by not associating these names with what they are doing, but by associating them with their function directly, will help keep you the concept in your mind. So how do you measure the connectivity of a graph? Well, sometimes the removal from a graph of a single vertex and all incumbent edges, right, produces a subgraph with more connected components. So sometimes if you remove a particular vertex and its corresponding all of its edges, it produces two subcomponents, two connected components that are completely more connected, right? So these kind of vertices whose removal results in two or more subgraphs is what we call the cut vertices, right, or articulation points. So if you put a cut on them, well, if you remove these vertices, it produces subgraphs that are more connected, right? So it basically they divide the. If you remove this vertex, it will divide the whole this vertex as well as its connecting edges. It will convert the whole graph into two or more. It will divide into two or more subcomponents, right? So subgraphs. The removal of a cut vertex from a connected graph produces a subgraph that is not connected. The subgraph itself is not connected. And analogously, an edge whose removal produces a graph with more connected components. Similarly, the cut vertices is when you remove a vertex and it produces a more connected component. On the other hand, if you remove an edge and it produces more connected components than in the original graph, that is what we call a cut edge or a bridge simply. So note that in a graph representing a computer network, a cut vertex and a cut edge represent an essential router. So a cut vertex is when you actually have an essential router. If you remove it, you cannot basically communicate with another part of the network. And the cut edge here is basically the essential link that if you remove or it fails for all computers, then they cannot communicate with each other. So that is what we call a cut edge or a bridge, which is as an essential link or essential edge itself. On the other hand, a cut vertex is a vertex which, when removed, it should disconnect the or remove, not get the connections ready for the whole graph. So, for example, in this graph, we can say that there are many different cut vertices. Is A a cut vertex? Well, A is not a cut vertex because if you remove it, the rest of the graph is still connected. Is B a cut vertex? Well, B is a cut vertex because if you remove it, you cannot communicate with A. Similarly, C and E are also cut vertices, right? So the cut vertices here are C and E. What are the cut edges? Cut edges are between A and B, I think, and between C and E. So those are the cut edges. So similarly, here's another graph. In this case, we note that C is basically cut vertex, and rest of them are not cut vertices, and there does not exist a single cut edge in this particular graph, right? So there are no cut edges. Let's talk about this one. How many cut vertices do there exist? Well, there does not exist a single cut vertex, right? And if we talk about cut edges, also there does not exist a single cut edge. So none and none for this. And that's the exact answer you can see over here. So, then we come on to another topic. So from cut vertices and cut edges. There's another thing that we call vertex cut. And again, these are two different things. Um, and this is something that we need to focus more on over here. Not all graphs have cut vertices. For example, the complete graph Kn, where n is greater than equal to 3, has no cut vertices. So for a complete graph like the one that we saw earlier, maybe it may not have any cut vertex at all. So when we remove a vertex from Kn and all edges instituted into it, the resulting subgraph is the complete graph Kn minus 1, which is again a fully connected graph, and hence there is no cut vertex. Connected graphs that do not have any cut vertex are called non-separable graphs. So that's by definition the name, and can be thought of as more connected than those with the cut vertex. Of course, if you can find a cut vertex, then there's at least a weak link there, and that link can be removed or can fail to cause disconnection in the whole network. But if a graph is non-separable graph, so there is no weak link, it does not have any cut vertex, then in that case it is more secure and it is more connected than the one that has a cut vertex. So of course we can extend this notion by defining a more granulated measure of graph connectivity based on the minimum number of vertices that can be removed to disconnect a graph. So the idea is simple. The minimum number of vertices that can be removed to disconnect a graph is what we call a vertex cut. So a subset V prime of the vertex at V of the graph G with vertex at V and edge at E is a vertex cut or separating set. So we call it a vertex set if G minus V prime results in a disconnected graph. So this is basically the subset removing which is going to produce a disconnected graph. And from that, we can define the term vertex connectivity. So remember, vertex cut and cut vertex is two different things. Cut vertex is a vertex which, if you remove, produces two or more disconnected components, right? On the other hand, a vertex cut is a set of vertices, the minimum number of vertices, which when you remove actually produces a disconnected graph. So from that set, we can define these notions, we can define the concept of vertex connectivity. The vertex connectivity of a non-complete graph G, denoted by this particular symbol of G, is as the minimum number of vertices in a vertex cut. So the minimum number of vertices that you can remove in a vertex cut, if you can define that, that is the vertex connectivity of a particular graph. So the larger this symbol is, the more connected the graph is, and this is very natural for a vertex connectivity. Right? So let's talk about this graph. What is the vertex connectivity of this graph? I think if we remove one vertex, for example, see, since this has a cut vertex, so the vertex connectivity of this is 1, right? What about this graph? The vertex connectivity of this graph is also 1, since we can remove C. What is the vertex connectivity of this graph? Well, the vertex connectivity of this graph is 2. You can either remove these two or these two to basically produce a disconnected graph. That is the exact definition for the vertex connectivity. Similarly, just like you had the cut edge, right, defined, then we can also define the edge cut in a similar way to the vertex cut and cut vertex. So we can also measure the connectivity of a connected graph G is equal to V in terms of the minimum number of edges that we can remove to produce a disconnected graph. So if, of course, a graph has a cut edge, then we only need to remove one to disconnect the graph. However, if G does not have a cut edge, then we need to look for the smallest set of edges that can be removed to disconnect it. A set of edges E prime is called an edge cut of G if the subgraph G minus E prime is disconnected. Of course, if you remove these all these edges, it produces a disconnected graph. And the edge connectivity of a graph, which is noted by lambda of G, is the minimum number of edges in an edge cut of G. So the minimum number defines the lambda of G. And this defines the lambda of G for all connected graphs with more than one vertex, because it is always possible to disconnect such a graph by removing all edges incident to one of its vertices. So we need to take the minimum, because if you remove all of the edges removed to an incident to one of its vertices, you'll basically produce a disconnected graph. So, but note that if G is not connected, then automatically the lambda of G is automatically 0. So we also specify that lambda of G is 0 if G is a graph that consists of a single vertex. Again, if it has not more than one vertex, then lambda of G is also 0. It of course follows that if G is a graph with n vertices, then the vertex cut for this is always going to be between sorry, the edge cut of this is always going to be between 0 and n minus 1. Hence, the maximum number of edges that are possible for a simple graph with n vertices is maximum n minus 1. So let's talk about the edge connectivity and the edge cut here. So what is the edge cut for this particular graph? Well, actually, since this has an edge vertex and an edge, so this has an edge, this has a cut edge, which is this point and this point. So we can remove one edge and produce a disconnected graph. So the edge cut value is basically 1. What about this one? Well, in this case, we have to remove at least 2 edges to produce a disconnected graph, and hence the edge connectivity value is 2. What about this one? In this case, we have to remove again 2 edges over here to produce a disconnected graph, and hence the edge cut connectivity value here is also 2. So what is the relationship between degree and connectivity? And this is very interesting, right? So the relationship between degree of a graph and the connectivity of a graph is very simple. The vertex cut value here, it will always be less than or equal to the number of to basically the edge cut value, and this will always be less than or equal to the minimum to the minimum degree of the vertex v. So it the vertex with the minimum degree, that is the maximum number of possible edge cuts that you might need to make, right? It is limited, it is bounded by that, and it may be even less actually, since it can be less, but it cannot be more than this particular bound. And similarly, the vertex cut will always, the number of vertices that you need to cut to produce a subconnected, a disconnected graph is always going to be less than or equal to the number of edges that you need to remove to produce a connected or disconnected graph, basically. So that is the relationship between degree and connectivity, and the edge connectivity as well as the vertex connectivity of a graph. So let's see some application of vertex and edge connectivity. Graph connectivity plays an important role in many problems involving the reliability of networks. For instance, we can model a data network using vertices to represent routers and edges to represent links between them. The vertex connectivity of the resulting graph equals the minimum number of routers that disconnect the network when they are out of service. So for example, it could be used in data networks. It could be used to know how many number of routers actually need to be out, and that is done by vertex connectivity. If fewer routers are down, well, data transmission between every pair of routers is still possible and is actually guaranteed. However, the edge connectivity represents the minimum number of fiber links, optic links, that can be down to disconnect the network. So if your links are down, it will still be possible for the data to be sent or transmitted through every pair of routers. And similarly, we can model a highway network as well. So this is again a different application of the same class, but this is very interesting as well. So we can model a highway network using vertices to represent highway intersections and edges to represent sections of roads running between intersections. The vertex connectivity of the resulting graph represents the minimum number of intersections that can be closed at a particular time that makes it impossible to travel between every 2 intersections. So if fewer intersections are closed, travel between every pair of intersection is still possible. The edge connectivity in this case represents the minimum number of roads that can be closed to disconnect the highway network. So if fewer highways are closed, it will still be possible to travel between any 2 intersections. Clearly, it could be useful for the highway department to take this information into account when planning road repairs. For example, it is also important to understand this from the perspective of Dharna people who are out there and who should know which roads to close, so that there is disconnectivity between 2 different portions of the city. At the same time, it is quite possible that everyone who is on a strike or something also knows. For example, in hospital, if there are multiple people who are working on a particular thing, then they must know that which people should be on leave or can be granted leave, so that there is no effect on the actual work that is being carried out. However, if that number increases to a certain point, then it may cause rush and problems for the incoming people. So of course, it has its applications in a lot of different fields and a lot of different applications. So let's move on with after these applications to some of the more conceptual topics, and one of them is the concept of a strongly connected versus a weakly connected directed graph. And this is what defines a connectivity in a directed graph. A directed graph is strongly connected if there is a path from A to B and from B to A whenever A and B are vertices in the graph. So for any two pair of vertices, there is always a path to and fro from both vertices. Then this is a strongly connected graph. So for a directed graph to be strongly connected, there must be a sequence of directed edges from any vertex in the graph to any other vertex, right? So of course, directed edges must exist from each vertex to any other vertex. A directed graph is weakly connected if there is a path between every two vertices in the underlying undirected graph. So it's not a strongly connected graph in the sense that it does not have a path to and fro from each vertex. However, still, if you take the underlying undirected graph, which we have discussed earlier, it will then produce connection between it will then produce paths between every 2 points. So that is a connected graph. So if you take the direction out by determining the underlying undirected graph, in that case, if it still produces a single component, then this is what we call a weakly connected directed graph. A directed graph is weakly connected if and only if there is always a path between two vertices when the directions of the edges are disregarded. And that's exactly if you disregard the edge direction, then this will produce an underlying undirected graph, and that's the exact definition. So clearly any of course strongly connected directed graph will automatically be a weakly connected graph. So let's take this example. The first example here is a strongly connected graph since there is always a path possible from each vertex to every other vertex. And hence this is a strongly connected graph. In any direction, you can consider to and fro, and in both directions you will basically find a path. However, on the right side graph, we see that from A we cannot actually reach B by following the directions. However, if we take the underlying undirected graph, then in that case, again, it produces a single component, and hence this is a weakly connected graph. So then we can talk about strong components of a directed graph. The subgraphs of a directed graph G that are strongly connected but not contained in larger strongly connected subgraphs, that is the maximal strongly connected subgraphs, are called the strongly connected components or strong components of G. So for example, in this case, note that if A and B are two vertices in a directed graph, their strong components are either the same or disjoint. Of course, they can either be the same or disjoint. So for example, in this particular scenario, we can observe three strong components of graph H. One is A. So if you remove A, well, we produce a strongly connected component, right? If you remove E, again, if you remove this E, again, we produce strongly connected components in terms of BCDE, BCDA, right? And finally, of course, the third component is BC and D itself. So that's also a strongly connected component. So that brings us to the next point, that how can we count paths between vertices? Well, let G be a graph with adjacency matrix A with respect to the orderings V1, V2, and Vn. So that's the ordering of the vertices of the graph. And it can actually have directed or undirected edges. It can have multiple edges, and loops are also allowed. So the number of different paths of length R from Vi to Vj. So that's the formula of how you can actually count paths between vertices. Is a very simple one. It's basically R is the positive integer, and if you want to say that it equals the ijth entry of A to the power R, and by A to the power R, we are actually multiplying the matrix with itself for R times. And whatever is the value in the ijth entry, that is the number of different paths of length R that are possible. So for example, if you want to find the number of different paths of length 5 from, let's say, vertex A1 to A5, then you just need to take the A1, A5th entry in the product matrix A to the power 5 to determine the number of different paths possible from A1 to A5 of length 5. And that is what is exactly shown here. So for example, let's take an example. How many paths of length 4 are there from A to D in the simple graph G? So this is a simple graph G, and we want to find how many paths of length 4 are possible from A to D. In this case, we just need to take, basically put it out as a matrix first, adjacency matrix. And after putting it out, we can raise it to the power 4 to determine the paths of length 4, and then simply take the entry, the AD entry in it, and that is going to give you the answer. The adjacency matrix of G ordering the vertices A, B, C, D, E is this. So that's a adjacency matrix. Then you raise it to the power 4. And the number of paths of length 4 from A to D is 1/4 entry of this. So we basically need to take the 1/4 entry of this, which is this one, and hence the answer is 8 in this case. So that brings an end to the lecture section 10.4 about graphs. And now we can talk about section 10.5, which is Hamiltonian and Euler paths, in the next lecture. So hope to see you again in the next lecture. This lecture was all about connectivity, strongly connected graphs, weakly connected graphs, directed graphs as well, how connectivity can be measured for directed graphs, and so on. And this was an interesting lecture in the sense that we'll be using some of these concepts of weakly connected and strongly connected components in the next few lectures as well. So with that, I'd like to thank you all for listening to this particular lecture. And I hope that you have understood most of the concepts explained in this lecture, and you'll be able to explain to actually combine those components and stuff with the portion that was defined earlier. So thank you very much, and see you again in the next lecture. Allah Hafiz.